Okay, thank you. Good morning, everyone. Yes, my name is Michele Bolognini. I'm a research fellow here at the Politecnico di Milano, and I've been working for 3 years in the Safe and Autonomous Systems Laboratory under the wise guidance of Professor Lorenzo Fagiano and together with my wonderful colleagues. And today, I'd like to show you one of the projects we focused on, which is based on one realization. We humans have the capability of building beautiful infrastructure, both in terms of art itself and in terms of its function. But of course, the other side of the same coin is that without maintenance, catastrophe is certain. So, of course, we already do maintenance on all kinds of infrastructure, but the technological advancement of maintenance is not as developed as you might imagine. This is just one of the types of inspections that are done on bridges. Suppose you have to inspect a bridge, you have to stop the traffic on top of the bridge, also possibly below the bridge, which represents a cost. You need to either buy or rent a crane, then you need to spend some more money to train some human personnel to do the inspection, and then you lift the human personnel that you saw costly trained in a risky situation. So this is not an ideal condition, and for this reason we decided to tackle the whole problem of inspection through drone-based technologies that should be ideally the most autonomous possible to relieve the human operators of the need to put themselves in risky situations. They should be insightful in that they would give you not only information on what goes on the surface of the building, but also below the surface itself to give you a more precise idea of the health status of the target structure. They should, of course, be accurate because accuracy and precision are absolutely key in a safety critical environment. And of course, if we want to substitute the current state of the art, they should also be, as a solution, cheaper than what we do today. So we started from assembling our own platforms and designing our own algorithms. This is a frame, a platform we assembled from a DJI frame, on which we mounted a couple of sensors, LiDAR sensor on the bottom, you see, to detect and also possibly avoid obstacles. And we also have an onboard computer that runs the motion planning and obstacle avoidance algorithm we designed. Yeah, this is one of the applications of one of our algorithms. This is navigation in a previous known environment. You see the drone, same on the left and on the right, navigating an environment for which it has no map, and at the same time creating a map and avoiding obstacles on its own based on the LiDAR sensors. You see, maybe it's a bit thin, but there's a complex area in which it moves at each time step. Those of you who dabble in numerical optimization know that complexity is a very nice property when you need to solve problems in real time. It makes solving problems way faster. Regarding the applications to the inspection of the built environment, one of the projects we focused on is the vision-based analysis of structure, modal analysis of structure. Modal analysis is a technique through which you study the modal parameters of a structure. That is, you study how it vibrates, the frequencies and the shapes of the modes of vibration. And in particular, you track the change of these parameters through time, different inspections. Now, we used markers in this case, but we ended up verifying that they are not strictly necessary. And we also ended up verifying that you can do that with cameras mounted on drones with an accuracy that is comparable to the one you obtain by installing accelerometers on the structure. Of course, that's the ideal case that is used today, but of course, installing accelerometers on a structure is pretty expensive if they're not already there, and maintaining them is expensive too. Second and final application to the inspection of buildings, if the computer can load the video, is the energy efficiency assessment of buildings. So here we use the drone off the shelf, readily available in any market with a dual sensor. So it's a sensor with two cameras, basically. One is a regular RGB color camera, and the other one is infrared. And what you can do when you have a camera that takes pairs of pictures in these two different frequency domains is use the infrared to detect if there are any problems on the energy front. So detect if there's humidity in the wall, for example, if there's some failure of the insulating layer. Then you can use the RGB pictures through known techniques used in this case, structure for motion. You can use them to build an accurate 3D representation, a 3D model of the building. And finally, you use the pair of RGB and infrared pictures and information you collected to actually locate in space the information and the defects you identified in the energy analysis. So this makes it easy to compare the model of the building as it is with the measurements. Time is up, so if you're interested in more, please feel free to reach out. I'll be here the whole day.